All right, our next topic with vectors and application of vectors is the notion of dot product. And to kind of motivate the dot product, I want to talk about work. We're trying to, with work, quantify the amount of effort it takes to move an object. And so if you think about what's it going to take to move something, I think that a couple of things that are going to come to mind are the force required and the distance that you have to move it, right? If it's something very lightweight, it doesn't take a lot of work to move it. If it's something very heavy that you have to apply a lot of force to make it move, that's going to be a lot of work. So we want our work to depend upon, oops, I got the wrong pen here. I want our work to depend upon the force, and we're also going to depend upon the distance that you move it. I'm in auto shapes. It's turning my D's into, let's turn off auto shapes. Turning my D's into a circle. Force and distance. So we're looking at force and distance. Should be related into work. And so if you've got if you've got a distance and you've got some sort of force that's applied, and we want to be smart about it, right? So what we're going to do is we're going to define work to be the magnitude of the force times the magnitude of the distance. So we're looking at these as two vectors. And then we also want to add sort of a smart component. We want to look at the angle in between those two, right? So if you're trying to move an object, what we want to look at is something that if you look at different values of theta, you want something that's maybe best. You want that angle to be 0 degrees, right? The smartest thing to do is to pull in the same direction that you want your object to move. And sort of the worst thing to do would be to do at a perpendicular angle. So you want something that at 90 degrees, so that maybe it's 1 is the best, or 0 degrees is best. At 90 degrees is not so good. If you're pulling at 180 degrees from where you want to go, well, that's kind of the worst. I mean, that's sort of negative. You know, you want to move something one direction, but you're pushing in the completely opposite direction in there. So if your angle between the two is 180 degrees, you're sort of doing negative work. You're moving things in the wrong direction. And then at 270 degrees, we're going to say that that's 0. You know, if you're pushing down, but you're trying to move the object to the right, that's absolutely, you know, you're not doing any work at all. It's not moving in the direction you want it to be. And then, of course, back to 360 is going to be 1. So I want something, a smartness factor, that behaves along these lines, that has this sort of curve to it, that has that behavior that it's a maximum at 0 degrees. At 90 degrees, it would be 0. 180 degrees, maybe -1 in there because you're going in the wrong direction. 270 would be 0, and then 360 back to 1 again in there. And of course, a nice function that does that is what? It's the cosine function. So we're defining the work to be the force times magnitude of the force times the magnitude of the distance times the cosine of the angle in between those. And we're defining that as the dot product, that F dotted with D would be the magnitude of F times the magnitude of D times the cosine of theta. Or more generically, you know, if you've got force and distance, mathematically, we're sort of separate those out. And if we just talk about some generic vectors u and v, we're defining this mathematical dot product of u dotted with v as the magnitude of u times the magnitude of v times the cosine of the angle that's in between those two vectors in there, as the dot product in there. So as a quick example here, if you're pulling a sled with a force of 15 newtons at an angle of 23 degrees from the horizontal, so our distance, we want it to move horizontally, this direction, 12.3 meters. But we're going to pull at a 23-degree angle. I want to pull at a 23-degree angle from the horizontal. If I look at the amount of work that we're going to do, it's going to be the magnitude of the force times the magnitude of the distance times the cosine of the angle in between those two, cosine of theta. And since we're doing horizontally there, our angle is going to be 23 degrees. I'm going to do 15 times 12.3 times the cosine of 23 degrees to get the amount of work that we've done in there. So we would get that to be, where did my calculator go? There's my calculator. All right, 15 times 12.3 times cosine of 23 degrees gives me 169.833. I think Newton meters is typically what we do that, or uh, the units that we'd use there. The amount of work would be 169.833 Newton meters in there. So in general, you're looking at the dot product, so that's the magnitude of the first one times the magnitude of the other one. A couple of things to note. Well, one thing in particular to note is that the result when you do the dot product, we'll sometimes call it the dot product is sometimes called the scalar product. And the answer is a number, not a vector in particular. So it's a scalar. It's just like a regular number. It's not a vector when you're done with this sort of things. So that's our dot product. And actually, let's keep going here. If you've got them in magnitude and angle, we've got a way to calculate them. Now, how about we look at the dot product where I've got u and v here, and what if those vectors are in component form? Well, we can work our way backwards, and we can find the two angles in there. We can look at maybe theta u, that's pretty bad, and theta v. Well, how about theta 2? Theta 2. So you got these two angles. So I know that if I want u dotted with v, I'm going to do the magnitude of u times the magnitude of v times the cosine of theta. And we can go ahead and we can find, the theta and subtract the two angles to find theta in there. But there's actually a little bit easier way to do this. So let's suppose that u is the vector AB, and v is the vector xy in component form. So if we have our vectors in component form, it's a little bit easier. There's an easier way to find the dot product instead of working out all the magnitudes. And let's look at that. So v, I said, was xy. So if we put our vector starting at the origin, the tip of it would be at the point xy, and u would be at the point AB. All right. And what I want to do is I want to look at the distance between those two vectors. Let's call it d, maybe there. So I know that d is, I can just use the distance formula. If I look at the distance formula, if you look at turning this into a right triangle, I know that the horizontal distance here is going to go be something like a minus x quantity squared, plus, and the vertical distance that we have here is going to be y minus b quantity squared. And so if we apply the Pythagorean theorem, we know that x minus a squared plus y minus b squared would be the square root, would be d squared in particular. And actually, that's what I want. I want d squared. I know that that's a minus x squared plus y minus b squared in terms of finding the d value in there. Okay, but we can also look at d with the law of cosines in mind, with the law of cosines in mind, I know that d squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of theta in there, right? So if I take the length of u and the length of v, I can apply the law of cosines to that and express d in that direction in that way. And so let's look at those two a little bit. Those two need to be equal to each other. Magnitude of u squared plus the magnitude of v squared minus 2 magnitude of u times the magnitude of v times the cosine of theta is equal to a minus x squared plus y minus b quantity squared. All right, let's simplify out this left-hand side. Let's start with that. A minus x squared is an a minus x times an a minus x. We got to use the distributive property, the extended distributive property, or FOIL to multiply those out. It's going to get kind of messy here, but that'll be all right. I'm going to get an a squared. I'm going to get from the firsts, the outers is going to be a minus ax, and the inners is a minus ax. And then I'm going to get a negative x times a negative x, which is a plus x squared. And then on the other side here, I'm going to get a y times y. I'm going to get a y squared. I'm going to get a minus by and another minus by from the outers and the inners. And then the last two is going to be a plus b squared. So the right side of the equation here is an a squared minus 2ax plus x squared plus y squared minus 2by plus b squared. All right, that's nice. Let's come back to the left side. How would you calculate the magnitude of u? Magnitude of u in particular squared, that's an a squared plus b squared, right? If I'm looking at a vector, I know that the magnitude of u is going to be the square root of a squared plus b squared. If we look at our right triangle here, I know that this distance is a along the x-axis, and b is the distance along the y-axis. So by the Pythagorean theorem, the magnitude of u is a squared plus b squared. Similarly, the magnitude of v is x squared plus y squared minus 2. And I'm going to leave it as the magnitude of u times the magnitude of v times the cosine of theta in there. All right, and so I have these two quantities that are equal to each other. Let's do a little bit more algebra with it. Let's subtract the a squared plus b squared from both sides of the equation. If I subtract an a squared and subtract a b squared, oh, they cancel off. Same thing happens if you subtract an x squared and a y squared, subtract an x squared and subtract a y squared, those cancel off. And what I'm left with is, I went a little too far there. Still a little too far. All right, let's see if I can control that a little bit better. I'm going to get a minus 2 magnitude of u times the magnitude of v times the cosine of theta on the left-hand side. And on the right side, I have a minus 2ax and a minus 2by. And what I can do is, to clean this up a little bit farther, is I can divide both sides by -2, divide by -2, or multiply by -1/2, and the -2 will cancel off on both sides. And I'll get the magnitude of u times the magnitude of v times the cosine of theta is equal to ax plus by. The negative signs will switch that from a minus to a plus sign. All right. But what is the magnitude of u times the magnitude of v times the cosine of theta? Well, that's just the dot product. So u dotted with v is equal to ax plus by. And if we go back and look at what a was and what y was, so an easy way to find the dot product, when you have things in component form, a is the x-coordinate of u, and x is the x-coordinate of v. So I'm going to do a times x and b times y in there, add those together, and that will give you the dot product. So we've got two ways to calculate the dot product. If it's in component form, if u dotted with v, I'm going to do, ax plus by. And if I have magnitudes and an angle, I can also do, it's the magnitude of u times the magnitude of v times the cosine of the angle in between the two in there. All right. So if I've got things in component form, if I have, say, u equals is the vector 3, 7, and v is the vector 8, -1. And if I need to calculate u dot v, it's super easy. It would be 3 times 8 plus 7 times -1. So 24 minus 7, which would give us 17, I believe. Yeah, 17 in there. And that would be the dot product of u and v. So it's super easy to find that dot product when the things are in component form. But we can also find it with this u dot v definition in there, sort of things. Okay, so dot product, magnitude of u times the magnitude of v times the cosine of theta, or it's the x components multiplied together plus the y components multiplied together in there. And a nice application of the dot product is work in there. That work is a nice way to think of that, how much effort you're putting into moving something, and it's the amount of force it requires and how far you're going to move it in there.